Hello, I am Ginevra Castellano. I'm an associate professor in Intelligent Interactive Systems at the Department of Information Technology of Uppsala University, where I'm also the director of the Uppsala Social Robotics Lab. And today I'm going to talk about research on socially intelligent robots. So according to a number of reports, robotics is now one of a few technologies that has the potential over the next few decades to have an impact similar to the one that the internet has today. And we can identify one reason. So until not so long ago, we used to see robots used in applications where they could be involved in tasks that people could not do or did not want to do. We see here some examples, robots used in military applications, deep mining, manufacturing. But today we see the rise of new scenarios where robots play new social assistive roles. Think about robots acting as instructors in the factory or tutors in the classroom, companions or personal assistants, tools for therapy. We have very different robots playing these roles, and here we can see some examples. They look very differently from the ones we saw before, and they also differ from one another. Some are more mechanical looking. We see, for example, this one. Some are more pet-like, some very human-like. This is an android robot, but they do share something. They have something in common. And what they share is a social and human-like appearance. So they, to some extent, look like humans. They may have a head, very simple facial characteristics, a body, arms. But if we think about robots having to cooperate successfully with humans, a human-like appearance is not enough. We need to develop skills for robots to engage successfully in natural interaction with humans. For example, robots need to be aware that they are interacting with the person. They need to be able to understand people's social signals and emotions in communication, in interaction, and also need to interpret this information in order to adapt to humans in a way that is appropriate to the context. So if we think about research in human-robot interaction, we can identify two main directions. So on one hand, we can focus on development of technical advances. We can push the boundaries of artificial intelligence to endow robots with computational skills that allow them to help humans. But we need to go beyond this. And another research directions in the area is to understand how humans interact with robots, how humans accept and whether they accept robots, how they perceive them. And also understand a little bit about ourselves. But why is it important to study this now? Well, we are witnessing an increased robotization in all areas of society. So in the future, starting already now, we need more trustworthy artificial intelligence and robotics. We need robots that put human at the center, and we need robots that adapt to the way humans communicate rather than the other way around. And since today we're talking about ethics, this is something that recently published European guidelines for trustworthy artificial intelligence emphasize. And that's something I'm trying to do. And at the core of my research are social behavior and emotion in human-robot interaction. So on one hand, in my lab, we develop computational models to allow robots with the skills to engage in natural interactions with humans in ways that don't force humans to adapt to the way robots communicate. And we also conduct human-robot interaction studies where human participants interact with robots, and then we can observe how people perceive these robots. So I chose an exemplar application to guide you through this. It's something that my lab has been working on for years, and this application is robot-supported learning. where robots act as educational agents to promote students' learning by providing social support and support to teachers in the classroom. At the same time, these robots, in addition to promote learning of students, they learn from students. They learn from interaction with other humans, how to best adapt to them. And that's what we call personalized adaptation. We used machine learning in order to do this. And I now guide you through 3 case studies to give you concrete examples of this work. The first involves a cat-like robot called iCat, which was made by Philips some years ago. And iCat, in this scenario, plays the role of a game companion for children in schools and teaches them how to play chess. And this is work conducted in the framework of the LIREC project, a European project that ran some years ago, on long-term interaction with interactive companions. So what capabilities does iCat have? Well, first of all, it knows at all times what happens on the chessboard. We have an electronic chessboard, so the robot can track what happens in the chess game. But this does not fully tell us about the experience of children throughout the interaction. So we develop a system using machine learning that could predict whether children at any time during the game were experiencing negative feelings. And by using this information, the robot could learn how to best support children or provide encouragement throughout the chess game. So in a way, we focus on an affective loop, so a loop where the robot can understand some information about the children's feelings and emotions, and also close the loop by generating behaviors that could also provide the social support. So we call this empathy in this context. And the robot plays a dual role. On one hand, it acts as a teacher, so it teaches children how to play chess, but on the other hand, it also learns through several interactions with people how to adapt to them, and that is done with machine learning. The second case study involves the use of robots as tutors to support children's learning and teachers in the classroom. And this is work conducted in the European project EMOTE that I coordinated a few years ago. And at the core of this project was the idea that robots could promote learning via empathy. As you can see in these images, our robotic tutors were a torso only version of the Now robot. That's a robot made by SoftBank Robotics. And the robot interacts with the students by means of a large multi-touch table where the learning activities are displayed. So in this context, the robot supports learning of geography. On one hand, we had map reading skills activities, but also sustainable development, how to build sustainable cities. And this robot was tested in early secondary schools in 3 main countries, UK, Sweden, and Portugal. Now here you can have an idea of what capabilities our robots were endowed with. In short, the tutors, robot tutors, were able to track students' progress and difficulties in learning, emotion throughout the learning process, and could also adapt to this by means of empathy and encouragement throughout the learning process. So we tested these robots in schools over different countries and observed long-term learning gains. And these videos can show you our tutors in action.
In the FP7 project, EMOTE, we are developing an empathic robot tutor with capabilities that allow it to engage in empathic interactions. To enable a robot to respond empathically, we need to model, interpret, and respond to the learner's affective state with appropriate expressive behaviour and pedagogical actions to the current situation. This requires a new channel for expressive behaviour using facial, gesture and posture recognition, supporting empathy in the learning context and increasing the learner's engagement. The robot assists the learner in completing tasks with a range of pedagogical actions. For instance, if the learner is frustrated and having difficulty with a task, the tutor will present the answer, explain it and move on.
The symbol is located somewhere over here.
And the final example of robot-supported learning consists of a robot acting as a tutor that promotes learning of the size, position, and relative position of countries in the world. And that is done via a dialogue-based map game, which is a cooperation between a human participant and the robot.
In this demonstration, we introduce a pedagogical reference resolution game, serving as a fun and engaging scenario to study repeated interactions with a social robot. The cooperative game we developed is designed to enhance people's geographic literacy when playing with a robot team partner. The players have the role of the tutor in this scenario. On the iPad, they see the world map with one country highlighted as the target. Their goal is to get the robot to select the same country on the shared screen, which is placed in between the two. The robot thus acts as a learner in the pedagogical game. Any verbal description, including the use of the country's name, is allowed to identify the target. The goal for the human-robot team is to score as many points as possible during the 10 minutes of game interaction.
So it's to the east of India and north of Australia.
Got it.
You got it?
Is it this one?
Yep, that's the one. Good job.
Nice.
So should we take the next one?
Yes. Let's move on.
All right, you remember where India was?
Yes.
So this country is bordering to India to the west of it.
Is it this one?
Yes, that's the one.
Yay!
Good.
We use the blended robot head fur hat as a robot platform for playing the game. The appearance of the robot can easily be changed by applying a different facial texture, making the robot look human-like, mechanical, or like a morph between the human-like and mechanical version, among others. The robot is...
So we're using this scenario to study the phenomenon of uncanny valley. So according to the uncanny valley hypothesis, people tend to like more increasingly human-like robots, but tend to dislike them as they approach but fail to achieve human likeness. Most research in this area is focused on people's reaction to pictures or videos of robots. There is very little work on real interactions and on how exposure and long-term interaction to robots may have an effect on perception of uncanny valley. And that is what our lab is working on at the moment in a project called COIN on coadaptive human-robot interactions. So we have found initial evidence that under certain conditions, the uncanny valley might be a transitory phenomenon. And what we're interested in at the moment is to investigate whether empathy abilities and emotional alignment skills, which I described earlier in the presentation, can affect perception of uncanniness by people over time. Now, I talk about the need for robots to adapt to the way humans communicate, rather than the other way around. So that is important for building trustworthy robots, but it's not sufficient. There are several other requirements that are very important to study, and one of them is transparency. So there is a lot of interest nowadays in transparent artificial intelligence and human-robot interaction as well. So at the moment, in an ongoing project called ANIMATAS, we are studying the effects on transparency on perception of a robot's mind. So does transparency affect people's perception that a robot might have intentional states? And this is really important because transparency will be more and more at the core of interactions between human and robots. And humans will need to be aware that they are interacting with an AI system. And the robot at the same time need to make people aware that it has certain abilities or certain limits. And you also need to explain why it makes certain decisions. And that's something that does not only apply to robots, but AI in general. So this is at the core of our research at the moment. And to conclude, the main message of this talk is we have seen that there is an increased robotization in all areas of society. So robots and humans in the future will interact more and more. So we need robots endowed with abilities that allow them to interact with humans so that humans don't need to adapt to them. In the absence of this, we might lose some of our humanity. And this process will go hand in hand with a very fundamental question, which is, what does it mean to be human? And this will be more and more interesting question as we assess our relation with technology in the future. And I want to say that this work is the result of a collaboration with students and researchers at the Uppsala Social Robotics Lab, but also with collaborators all around the world. Thank you.